Hi, good morning all. So I'm presenting this presentation on behalf of Amir, Mardani, and Alireza Malmali. So this presentation looks at power supply designs using multi-phase buck-boost converters as opposed to conventional buck-boost converters for rack-level design and server-level PSU design. Oops. So going over the headlines, we look at the traditional design of the power supply unit, the design of a buck converter, which is conventional. Then we look at the synchronous buck converter design, going towards multi-phase, and then look at the experimental results, and finally, the conclusion. So traditionally, a lot of power loss happens in the actual power conversion phases during initial power conversion, distribution, and cooling. And of course, because the output power is much lower than the input power, we use buck converters. So in order to increase the efficiency of these power supply units, we look at multi-phase synchronous buck converters. So as you notice in the diagram, this design is for a server-based multi-phase synchronous buck converter, but it can also be applied to a rack-level design, feeding a 48-volt or a 12-volt bus system. So as opposed to a conventional buck converter, synchronous buck converter adds an additional MOSFET in place of the pass or the flyback diode. However, this increases the complexity as we have one more switching unit we have to control. But it allows for lower power losses, controllable duty cycle, and a higher power range for control. Although this design is a little bit more complicated, the multi-phase system can take these disadvantages and actually use them in their favor. So taking this design and then stacking it in a series of four for 4 different phases, we're actually able to apply a 90-degree phase shift using a microcontroller for the switching MOSFETs, and ultimately lower the voltage and current ripples, increase the efficiency by a factor of 3 to 4%, and this allows for lower stress on the MOSFETs for each phase. And then with this design, we have very fine control of the duty cycle parameters for the switching power supply. The downside of this, however, is that there's more cost because now we're effectively quadrupling all the components and increasing the surface area and total volume required for this. Now onto the results. So this was realized in a lab environment using conventional off-the-shelf parameters and using a 48-volt input, which would be coming from some power distribution unit. Output 12 volts, and then we see we have a switching frequency of 250 kilohertz with a total efficiency of roughly 99%, so 98.71%. So comparing the efficiency from conventional converter to a synchronous converter, we do see that increase in efficiency. Perhaps the biggest benefit of this is that we have much lower current and voltage ripple on when we go from a synchronous to a multi-phase synchronous buck converter. So we see that here we have quite a bit lower output ripple. So in conclusion, using a multi-phase synchronous buck converter, we have effectively a higher power rating, a higher efficiency conversion, lower heating losses because we are now splitting into multiple phases and doing that conversion there, and we have lower stress on the actual passive and active devices that are in the power supply unit. So that is the conclusion of the presentation. So any questions that may be had for this group, please let me know. I'll be upstairs with the poster presentations, and then we can work on sending those questions back to the authors or any comments or feedback. Thank you.